Okay, our problem reads, the cheetah is one of the fastest accelerating animals because it can go from rest to 27 meters per second in 4 seconds. If its mass is 110 kilograms, determine the average power developed by the cheetah during the acceleration phase of its motion. All right, so this sounds like it's got maybe a lot of stuff wrapped up in it. We're interested in the power of the cheetah. So let's remind ourselves that the power of that cheetah is going to be equal to the work divided by the time that that cheetah is doing that work. We know that time is 4 seconds. So we know, we're told that the cheetah goes from rest to 27 meters per second in 4 seconds. So we have our time variable. So we need to know the amount of work that that cheetah does. Okay, well, work, remember, is the force times the distance times the cos. Well, it's the dot product. I'll do the dot product first, which is force times d times the cosine of the angle. Now, if we imagine this cheetah running, it's my, there's my really fast cheetah. Yeah, just go with me on that one. All right, so if we imagine the cheetah running, the force exerted by the cheetah it's the force of the cheetah's feet on the earth and the earth pushing back on the cheetah, but they're the same. So let's think about the cheetah as being like a little engine. So the cheetah is exerting, the engine of the cheetah is exerting a force, and it's going to be along the same distance that the cheetah is running. Now, there's a couple approaches that we can take for this problem. We could do kinematics. We know that we are going from an initial velocity of 0 to a final velocity of 27 meters per second. So I could determine the acceleration of the cheetah, and then from that acceleration, I could determine the force that must be causing that acceleration. There must be a force acting on the cheetah. It's actually the cheetah's feet on the ground. It's a frictional force, a static frictional force, but that's equal to the ground's force, the force of the ground on the cheetah is equal to the force the cheetah is exerting on the ground. Those are equal. That's going to be related to the force that's doing the work. That's one way to do it, kinematics. But we've also learned some powerful additional ways to do things, one of which is the work-energy theorem. So remember what the work-energy theorem tells us. It tells us that the net work is equal to the change in kinetic energy. Now that's the net work. We're only going to really look at the work along the direction of the distance that the cheetah is going, because there's nothing happening between the normal force is doing no work and the force of gravity is doing no work because it's not in the direction of the motion. So the net work then is going to equal the final kinetic energy of the cheetah minus the initial kinetic energy of the cheetah. And we have no external forces acting on the system. So we have 1/2 the mass of the cheetah times v final squared minus 1/2 the mass of the cheetah times v initial squared. All right, so I have all that information. I know my mass of the cheetah is, what was the mass? 110 kilograms. Its final speed was 27 meters per second squared minus 1/2 110 kilograms times its initial speed, which is 0. So this gives us, and I need to grab my calculator. All right, so this gives us a change in kinetic energy of 0.5 times 110 times 27 squared of 40,000, excuse me, 95 joules. So that is our work. All right, so I know my work, and now I can do my power relationship, which is work over time. And my work is 40,000. I'll just put in the full number since we'll round at the end, divided by my time of 4 seconds. The power of the cheetah is 10,000 watts. All right, so again, you could do kinematics. You could do kinematics. If we did that kinematics, we would, in theory, come up with the exact same power. We should come up with that same power. Or we can jump right to that, utilizing that idea of energy and work energy to see that it must have taken work to change the kinetic energy of that cheetah from 0 to 27 meters per second. How much work did that take? And then use that directly to get our power. Okay, nicely done.